When two events occur simultaneously, the occurrence of one event will not disturb the other. Such events are called as independent event. Probability of occurrence of at least one of A and B means it is P of A or B, which is nothing but probability of A union B. If the product of their respective probability is not equal to probability of E intersection F, then we say that they are dependent events. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, Vidhyaashram School of Excellence, Mysuru. So here in this session, we are going to extend the concept of probability by learning the multiplication theorem on probability, and we will study about independent events. So let's take multiplication theorem on probability. In our previous session, we have learnt about the conditional probability, that is probability of A given B has occurred is given by probability of A intersection B divided by probability of B. Now, if we need the probability of A intersection B, we know that A intersection B is simultaneous occurrence of two events at the same time. So, with the help of conditional probability, we can write this as probability of B dot probability of A given B. Similarly, we can also write probability of A intersection B with respect to probability of A dot given probability of B given A is already happened. Since we have used the product here, this condition is nothing but the multiplication theorem on probability. So, let E and F be two events associated with a sample space S, provided probability of E or probability of F is not equal to 0, it has to be greater than 0. Then simultaneous occurrence of E and F is given by probability of E into probability of F given E, or probability of F dot probability of E given F has happened. So this above result is known as multiplication theorem on probability or multiplication rule of probability. So here I have taken two events here. The concept of this multiplication theorem can be extended to n number of events also. Now here I have taken three events. E, F and G are three events of the sample space. We have probability of E intersection F intersection G, that is the simultaneous occurrence of all these three events is given by probability of E, probability of F given E is happened, probability of G given E intersection F is already happened. So this E intersection F can also be simply written as EF. So the same thing we can extend the concept of probability of E1 intersection E2 intersection until En in such a way that, so this is probability of E, probability of E2 given E1 is happened. Next, probability of E3 given E1 and E2 is happened, and similarly we can extend the product up to En, so En minus 1 etc. So like this. So we can extend this multiplication theorem to n number of events given E, F, G are the events of the sample space. In the same way, E1, E2, En are the events of the sample space S. Now let's take an example here. Three cards are drawn successively without replacement from a pack of 52 well shuffled cards. What is the probability that the first two cards are king and the third card is an ace? Now we know that when we talk about cards, we have 52 cards in a pack. So now the first two cards which we will take has to be king and the third card should be an ace. We know there are 4 kings and 4 ace out of 52 cards. Now let me take the probability of the first card is king. So let K represents king and let A represents ace. Now what is the probability of getting king card? So that is equal to 4 by 52. Now one card is already taken out from 52. So that is I have taken a king card. So there are left with 51 cards. Now since the question is asked without replacement, I'll not put back the card here. So I have taken out one card which is king. So now this event is already happened. Let me consider the event where I have to take one more king given I have already taken one king out of the cards. So now the remaining cards are 51 and there are only 3 king cards out of 51 cards. So therefore, it has to be probability of taking king in the second event, so that even in the first event I have taken the card king. So it has to be 3 divided by 51. Now I have taken 2 king cards. First card is a king, second card is a king. So now there are only 50 cards in a pack. So now the next thing is the third card should be an ace. I have to take an ace where I have already taken 2 cards from the 52 cards. So there will be only 50 remaining cards and out of that I have to take ace. So we have 4 cards for an ace. Now, therefore, the total probability using the multiplication theorem so we can write it as 4 by 52 into 3 by 51 into 4 by 50. So if we evaluate this, you will get the value 2 divided by 5,525. Next question. 2 balls are drawn at random with replacement from a box containing 10 black and 8 red balls. Find the probability that both balls are red. First ball is black, second is red. One of them is black and the other is red. So 2 balls are drawn means after taking one ball, we will replace it back. So clearly they have given here the problem with replacement. The previous problem was without replacement. So in each event, the number of cards were going to be less. But here, the balls will be same throughout the experiment here. So therefore, first let us take one ball from 18 balls and that has to be red here. And it says the second ball must be red with the replacement. So let us take the first problem. So probability that both are red. Now I will draw one ball out of 18 balls and probability of taking red ball is 8 out of 18. Now once you take out a ball, you will put it back again. So again there is 18 balls where 10 black balls and 8 red balls. Now I have taken the first drawn ball as red, again the second drawn ball. So using multiplication theorem on probability, we need to take the product here. So once you replace it back, again we are left with 8 red balls and out of 18. So therefore, the total probability, that probability of both are red is 8 by 18 into 8 by 18. So on solving this, we'll get the value as 16 by 81. Next, to the second case, here the probability is first black and second red. Now, consider that we have 18 balls now. The first ball should be black. So, how many blacks are there? 10 blacks are there out of 18. So, I have taken the probability as 10 over 18. Now, once I have taken one black ball, then I'll replace it back. The total number of balls is again 18, but my second drawn ball must be red. So, there are 8 red balls. So, therefore, it is into 8 by 18. So, therefore, here the total probability value is equal to 20 divided by 81 on simplification. Next, the third says one of them is a black and the other is red. So, they have not specified here. The first one has to be black and the second one has to be red. So, it can happen in any other. So, the first ball black, second ball red, or first ball red, second ball black. So, therefore, here for the third case, probability that one of them is black and other is red. So this can happen in such a way that it may be the probability of red or probability of black, or so probability of black and then probability of red. So here we need to calculate the probability of red ball. So it is 8 by 18 and probability of black is 10 by 18, or means plus. So probability of black 10 by 18 into 8 by 18. So it can happen in one of the way. So either red or black, or either black or red. So therefore, this is the total probability of the given condition. So on simplification, the value will be 40 divided by 81. The next concept is independent events. So what do you mean by independent events? E and F are two events such that the probability of occurrence of one of the is not affected by the occurrence of other. Such events are called as independent events. So when I talk about the conditional probability, so we will impose a condition that we need to find out the probability of an event A where event B is already occurred. So here the event A is affected by the event B here. So therefore the probability value changes with respect to probability value of A when it is given in terms of conditional probability. But here when we talk about the independent events, when two events occur simultaneously, the occurrence of one event will not disturb the other. Such events are called as independent event. If we extend this concept irrespective of the conditional probability, we'll get here. So the probability of F given E is happened is same as probability of F. And if we consider probability of E given F has already occurred is same as probability of E, provided they are non-zero probabilities. So in other words, using the simple definition, the probability of occurrence of simultaneous events is the product of their respective probabilities. That is, let E and F be the two events associated with the same random experiment. Then E and F are said to be independent if probability of E intersection F is equal to probability of E dot probability of F. So here when I say the conditional probability, probability of E intersection F will be equal to probability of E probability of F given E is already happened. Since they are independent event, since the occurrence of E is not affected with respect to F, so probability of F given E is same as probability of F itself. So therefore, the simultaneous occurrence of events E and F are equal to probability of E into probability of F, given that only if they are independent events. Otherwise, we'll consider them as dependent events. So, if the product of their respective probability is not equal to probability of E intersection F, then we say that they are dependent events. Thus, we say that the simultaneous occurrence of the two events is same as the product of their probability. So, such events are called as independent events. Now, we can also extend this concept with three events which are mutually independent. That means A intersection B, B intersection C and A intersection C will be equal to their product of their respective probabilities. That is, if A, B, C are mutually independent events, then probability of A intersection B is P of A into P of B. Similarly, probability of A intersection C is P of A into P of C. Probability of B intersection C is P of B into P of C, and hence probability of A intersection B intersection C is P of A dot P of B dot P of C. So the concept of multiplication theorem is extended in terms of independent event, and hence we can define this until n number of events if they are mutually independent events. Now let's take problems. If P of A is equal to 3 by 5, P of B is equal to 1 by 5. Find P of A intersection B if A and B are independent events. Clearly they have given their independent event. So therefore, probability of A intersection B is product of probability of A, probability of B. So therefore it is 3 by 5 into 1 by 5, which is equal to 3 by 25. Next question. A die is thrown. If E is the event, the number appearing is a multiple of 3, and F be the event, the number appearing is an even. Find whether E and F are independent. So to find E and F are independent, we need to check this. The probability of EA intersection B is same as probability of A into probability of B. Similarly, here event E is given. So they have given it is the number appearing is a multiple of 3 when a die is thrown. So that is 3, 6. So probability of E will be 2 by 6, which is equal to 1 by 3. Next we are given with event F, which is an even number. So 2, 4, 6. So probability of F is 3 by 6, which is equal to 1 by 2. Now let's consider E intersection F. E intersection F is 6. So probability of E intersection F is equal to 1 by 6. Now consider P of E dot P of F, that is 1 by 3 into 1 by 2, which is equal to 1 by 6. So clearly if you consider it as 1 and 2, from 1 and 2, probability of E intersection F is equal to probability of E into probability of F. Hence, they are independent events. Next question. If A and B are two independent events, then prove that the probability of occurrence of at least one of A and B is given by 1 minus P of A dash into P of B dash. So, probability of occurrence of at least one of A and B means it is P of A or B, which is nothing but probability of A union B. So that is equal to probability of A plus probability of B minus probability of A intersection B. So they have given A and B are independent events. So therefore here, instead of probability of A intersection B, we can write P of A into P of B. So from these two terms, we can take probability of B as a common factor, then we are left with 1 minus P of A. We know that 1 minus P of A is the complement of the probability A dash. So therefore, probability of A plus probability of B, this can be written as probability of A dash. Now again, probability of A can be written as 1 minus probability of A dash. So plus probability of B, probability of A dash. Now again, 1, take minus outside. We can take probability of A dash as a common factor. Then here I am left with 1 minus probability of B. Now here I have 1 minus probability of A dash, 1 minus probability of B means 1 minus probability of B dash. So therefore, probability of the occurrence of at least one of A and B is given by 1 minus P of A dash, P of B dash. Next question. Probability of solving specific problem independently by A and B are 1 by 2 and 1 by 3 respectively. If both try to solve the problem independently, find the probability that the problem is solved. So clearly they have given their independent events. I need to calculate the probability that problem is solved. So here I'll take the probability of problem is solved in terms a complementary as 1 minus probability problem not solved. So because when I say probability is solved, it may be solved only by A, or it may be solved only by B, or it may be solved by both simultaneously. So therefore, when I say probability is not solved, it is neither solved by A nor solved by B. So calculating probability of solved is complicated when compared to calculating the probability of not solved. So therefore, here the probability of problem is solved is taken in the form of 1 minus probability of problem not solved. When I say not solved here, probability is neither solved by A. So if I take A, they have given it is 1 by 2. Probability of A is 1 by 2. That means the problem solved by A, the probability that the problem will be solved by A is given as 1 by 2 and by is given as 1 by 3. So here I am not taking that, I am taking opposite to that. So probability is not solved by A as well as B. So it has to be probability of A dash intersection B dash. So it is 1 minus probability of A dash intersection B dash. Now since clearly they have given independent events, that is A and B are independent events. So A dash and B dash. So A dash and B dash. So if A and B are independent, then A dash and B dash are also independent events. So therefore here I can write this as product of A dash into B dash. So now we know that probability of A dash can be written as 1 minus P of A and this can be written as 1 minus P of B. So here we have 1 minus 1 by 2, 1 minus 1 by 3. Now that is equal to 1 minus 1 by 2 into 2 by 3. So here 2 get cancels. Again 1 minus 1 by 3 will become 2 by 3. So therefore probability that the problem is solved is equal to 2 by 3. Next question. Given two independent events A and B such that P of A is equal to 0.3, P of B is equal to 0.6. Find probability of A and B, probability of A and not B, probability of A or B, probability of neither A nor B. Since A and B are independent events, so not B, not A are also independent events. So when I say all these are independent events, then their probability of occurrence of the simultaneous events is equal to the product of their respective probability using the definition of independent event. So probability of A and B can be written as P of A into P of B. So that is equal to 0.3 into 0.6, which is equal to 0.18. Next we have probability of A and not B, that is probability of A and not B, which is equal to probability of A dot probability of B dash. So probability of A is 0.3 and B dash is 1 minus 0.6. So when I say 1 minus 0.6, it is 0.4. 0.4 into 0.3 is 0.12. Next, similarly, we have A or B, which is probability of A union B. So here I can write this as P of A plus P of B minus probability of A intersection B. Now here, since given their independent event, now substituting the value here, we can write 0.3 plus 0.6 minus, we have already found probability of A and B here, so whose value is 0.18. So therefore, this is equal to 0.72. The last one is probability of neither A nor B. So that is equal to probability of A union B whole dash, which can be written as 1 minus probability of A union B. So 1 minus probability of A union B is given as 0.72. So therefore, this is equal to 0.28. Now this problem can also be taken in the form of probability of A dash into probability of B dash also, because clearly they have given These are independent events. So we can find probability of A dash, probability of B dash, and then multiply them. We'll get the same answer. The next problem is a die is tossed thrice. Find the probability of getting an odd number at least 1. So probability of getting odd number is the complement of probability of getting even number. So first, I'm calculate probability of getting an even number. So probability of getting an even number once a tossed is thrice is 1 by 2. So thrice means it is 1 by 2 into 1 by 2 into 1 by 8, which is equal to 1 by 8. So now probability of getting odd number is the complement of probability of getting an even number. So therefore this is equal to 1 minus 1 by 8, whose value is 7 by 8. So in this session we have learnt about the multiplication theorem on probability as well as independent events. I'll meet you in the next session with the new concept. Until then, keep watching, keep learning and keep exploring. Thank you.